introduction, showing all this algebraic structures and also the tools. And I told you yesterday that mainly the tool is, we start with a K algebra, where K is a field. And to deform this algebra, one has to change the field K to the ring of formal power series, Kt, where T is the parameter. Okay? And of course, if you do this, then you need also to introduce this A, which is a K vector space. Then this is changed to the formal space AT, which is the set of elements of the forms, the sum of A, K, T to K, K larger or equal to 0, and where A, K are elements in A. Okay, and we have seen that this AT in some cases, at least for this AT, if in A is finite, then we can. Then AT is isomorphic to A tensor KT. Okay. One should say also that this KT is local. One of the properties here, if the constant term is non-zero, then you have an inverse for a formal power series. This is a well-known property, and this could be interpreted that KT is a maximal ideal. And the only one. And now to deform deformation, of A is of A, let's say with multiplication mu 0. This is the mu 0 is the multiplication here. It is given on AT by a formal multiplication which we can write mu t equals to mu 0, the original multiplication, plus t mu 1 plus t squared mu 2, etc. Okay? And where this mu i's are mapped from A cross A to A. Okay? And then they are just bilinear maps. Okay? And now we will try to see and provide the conditions on this mu i's, because we need also that such that here, let's complete the definition, such that ut is associative. Let's say formally associative. I will express this. Now, what does it mean? Then mu t is associative. This is equivalent to say that for any formal multiplication, which is kt linear. Then maybe I should complete here and say, which is by a formal multiplication mu t, which is kt bilinear, and where these mu i's are bilinear maps. Maybe now it's complete. And saying that mu t is associative.
So what is exactly the way that this induces the multiplications on a? So the
you mean mu t?
Yes, mu t.
Yeah, that's mu t if that okay. Then mu t is a map from AT cross AT in AT.
Yeah, but in terms of the
which means that here, if I take a sum of A T A like this, okay, and the sum of B J T J, then this is mu t of the sum A I T I B J T J. Okay, and since mu t is kt linear or bilinear, okay, then this mu t of sum of I A I T I sum J B J T J, and this is the same as double sum over I and J of TA T to
as a bilinear, you can take all the sum out of the.
yes, the sum is out now, and T also could be out. T plus J mu T of AI Bj. Okay? And according to the definition mu t, and this is the sum, the double sum of I bigger than 0, J bigger than 0 of T to I plus J, and here we have a sum of K from 1 to infinity of mu K AI Bj.
To the T to the K, maybe. T to the K.
Yes, T to the K. But T to the K you can also put it here. No.
No, because the K.
No.
So you have
Okay,
to take
that's
the index also.
Yeah. Okay. That. And let's see it. K from 1 to infinity to R plus J plus K. Like this. Zero, sorry. Okay?
No, this is very clear now.
Yeah? Okay, thank you. Okay, then now you can see that that it's enough to know this. Then I can just consider. Then we can consider mu t now from A cross A to AT. And then here for say, let's say AB, we associate a sum of T to K mu K AB. k that are equal to 0. And this is the deformation. You can see that for t equals 0, then mu t is just mu 0. And it degenerates to mu 0 when this parameter is 0. And of course, when the parameter is different from 0, it gets something new. But of course, this mu t should satisfy the associativity condition. Then mu t should satisfy the associativity condition which we can write like this: mu t of a, b, c. This should be equal to, let's write it directly, minus mu t of a, mu t of b, c equals 0. Okay? And this is what, let's label it 1, and it's called the deformation equation. Okay? And we have to solve this equation to get what will be this new case, in order to get a deformation of this mu 0, which is associative. Now let's write things. Then this mu t, then this is equivalent to here we have a sum. Can get a double sum. Then this is mu I, mu j. Okay. T to I, mu I of, and here mu j. Then you have a sum over I, sum over j, mu I, mu j of a, b, c. Okay? And the same here. And this is minus mu I, a, u, j, b, c. Okay? And this should be 0. Okay? I replace each ut by some like this. And then what I get here is this. Then we have a formal power series, which is 0, like for polynomials. It's 0 if each coefficient is 0. Then this equation, in fact, is equivalent to an infinite system. Then this is equivalent to, okay, then I could write it in a different way. And this is a sum over p equals 0 to infinity of a sum over j. Then here I put just e equals to I plus j. And this is t to p this is mu r mu p minus I of a b c minus mu I of a mu p minus I of b c. Okay, this equals 0. And I goes from 0 to p. Okay, this is a different way to write this. And now let's see what happened for small p's. And for example, for what happened for p equals 0. Then this is okay, but this is This is a system. Huh? And this system, no, not yet. Sorry. It's not yet a system. Now this is equivalent to a system. Then each coefficient here should be 0. Then this is a sum. Maybe it's better to write P here, T to P, then it becomes more clear. Then the coefficient now is this sum. The coefficient of T to P is this sum, and it writes as a sum from 0 to P of mu I, mu P minus I, A, B, C, minus mu of I, A, mu P minus I of B, C. Okay? And this should be 0, and this should be 0 for P equals 0, 1, 2, etc. Okay? And now for P, what is this? What is the equation for P equals 0? We have a sum from 0 to 0, and it's mu 0 of A, B, C minus mu 0 of A, mu 0, B, C. Which will be 0. What is it?
Associativity.
It's the associativity condition. The first term, here there is the associativity of mu 0. And since A is associative, then this is satisfied. Okay? Now, what happens for P equals 1? Then for P equals 1, it goes from E0 to 1. Then it writes as mu 0 of mu 1 A, B, C minus mu 0 of A, mu 1, B, C, and plus the sum for I equal 1, mu 1 that's right, plus mu 1 of mu 0 AB C minus mu 1 of A mu 0 B C equals 0.
But here we can cancel. Oh no, we can.
Nothing can. And who can see what is this? What does this condition means for mu 1? Because the unknown here is mu 1. Then, if you remember well, the talk by Anita, and what I recalled yesterday, and this is connected to cohomology. Sorry? Yes. Now this means exactly that the delta 2. Huh? Yeah. This is equivalent to delta 2 respect to the Homological homology of mu 1 is 0. Which means that this mu 1 is a cocycle. Okay, then this is the first connection, and this is the first important result in this deformation theory. And if you want to construct a deformation, then you have to to consider for your first term, you need only to pick them from the cocycles, not elsewhere. And this is the first theorem obtained by Gerstenhaber. Then let A mu0 be the associative algebra, to be unital, of course, and we will see also a property for unital algebra later. And ut be a deformation, a formal deformation, ut equals the sum of T2k to k, and if it could be that mu1 should be 0, if mu1 equal mu2 etc. to mu p minus 1 is 0, then the first non-trivial term, then mu p belongs to is a two-cocycle. This is a little bit more general than what I mentioned there. And what I mean here is that if your mu1 is 0, mu2 is 0, mu p minus 1 is 0, the first term, which is non-trivial, this should be a two-cocycle. Okay? Then this is the first and very important observation. Okay?
So it says that mu1 is 0, then mu2 must be a two-cocycle. If mu1 is 0, then mu2 must be a two-cocycle.
Exactly. This is exactly the sense of this theorem. Okay? And now let's go further and see how to write the elements of this equation. Now, what happened for any p? Then for p, we can rewrite. We can write this equation in a different way. Now, if I pick the first term in the sum and the last one, then I could write if the first for I equals 0, then I get mu0 of mu p then mu p of a b c minus mu0 of a mu p b c. And now I take the last one, and the last one is plus mu p mu0 of a b c minus mu p of a mu0 b c, and this should be equal to minus the sum. But now the sum is from 1 to p minus 1 of this mu I mu p minus I of a b c minus mu I of a mu yes the okay, and what about this term?
This is again some element of cocycle.
Yeah, it's again mu p is a two-cocycle. This is again delta 2 of, and now we can use also we can use also a notation introduced by Gerstenhaber, this circle notation. if you remember, I denoted by phi composed by psi, this Gerstenhaber circle. Now, if phi and psi are two quotients, then this applies to three elements, and this is phi of let's say psi of AB minus C minus phi of A psi of BC. You remember this notation from Gerstenhaber? And now I can denote this system. Then this system 2 could be now written as 2 is equivalent to the system which I could write delta 2 of mu p equals to minus, and here it's a sum of mu I Gerstenhaber circle mu pi minus so I running from 0, not 0 but 1 to p minus 1.
What is delta 2 of mu p? What is mu p?
Mu p is then this term here in the left hand side. This is exactly delta 2 of mu p. Yeah?
Yes.
Okay. And this right hand side, I denote it using I write it using this Gerstenhaber circle. Then it becomes this. Then now we can also introduce the notion of truncated deformation. Then definition: if mu t equals mu 0 plus t mu 1 plus t to p mu p, if it's truncated, then we say that this deformation is of order p.
Of order p.
Yes. It's a sort of polynomial deformation. We say that mu t is of order p of order p. Now let us assume that we have a deformation of order p. Now assume that we have a deformation of order p. That's deformation. Let's denote it like this. Of order p. And then we aim to extend it to a deformation of order p plus 1. Then we aim to extend it to a deformation of order p plus 1. Okay. Then if this mu t p is an associative deformation, then this means that all the equation up to the p plus 1 first equation are satisfied. What we removed, it removes only one condition. Then the only condition to be checked is mu not mu but delta 2 of mu p plus 1. This should be equal to a sum from I running from 1 to P of mu R composed by, this is Abdenacer circle, by mu P minus I. Okay?
E plus 1 minus.
Yes, thank you. Okay. Then we, if we look at this term, this term depends on the elements. Let's call them elements mu1 to mu p, which are in my first deformation. And the term what I want to add. Then here my deformation now is mu t for p plus 1. This is mu 0. This is mu t p plus mu plus t2 p plus 1 mu p plus 1. Okay. Then I want to add this term to extend my deformation. Or one order further. And what is the condition on this? Then this is delta 2 mu p. And it turns out that if we call this obstruction, the obstruction is here. If I could find mu p plus 1 such that delta 2 of mu p plus 1 equals this term, which depends only on the elements of mu 1 to mu p, then I'm done. I could extend my deformation. And now let's look at this term. In fact, this is called minus is here. This is called the obstruction. We call this term obs. And it depends on mu 1, mu p. And it turns out that the proposition here is if this term, if we compute delta 3, because this is a 3, if we look at it as a quotient, is a 3 quotient, because it applies to 3 elements. Now this is in C3AA, right?
Which is the quotient in 3 elements?
No, this term. Because this applies, if you remember, to ABC. Then this is a trilinear map. This ops is a trilinear map. Is it clear? Then if you compute now the third cohomology, or compute delta 3 of this ops, it turns out that it's 0. Which means all these terms, this belongs to three-cocycles.
But why is delta 3 of ops equal to 0 from this equation?
No, from a proof which I didn't do here. But you can prove it. I mean, the proof here it's based on the fact that if you take delta 3 of f circle G, just have a circle, and you can prove that this is delta 2 of f circle G plus f circle delta 2 of G. This is the main tool to show that Then the abstractions are three-cocycles. Now, in order to get our deformation extended, this should be a three coboundary. Then we can extend we can extend the deformation if the abstraction is a three-boundary.
This is another claim.
No, I mean it's clear because why? Here we have this term, which is a three-cocycle, which means that delta 3 is the ups. But if we could write ups as delta 2 of some phi, then this phi could be my mu p plus 1. Huh? Then from this we can derive the second theorem. And if H3 of AA is 0, if the third homology is trivial, then every deformation of order P could be extended to a deformation of order P plus 1.
H3 is 0.
Yes. Then every deformation of order P of order P can be extended to a deformation of order P plus 1. Why? Because we know already that this obstruction is a three-cocycle, but since all three cocycles are three-boundaries, we can get our phi. Okay?
And there will be unique phi. There will be unique phi in that case.
Up to it's not unique up to a boundary, huh? But we will see about this. Now it's okay. Then this is about the abstractions. Now we can address the question about how we can identify equivalent deformation. What does it mean, equivalent deformation? Huh? Now, new section, equivalent and the trivial deformation. Now we consider we still have this algebra over K with defined with multiplication mu 0, and now consider two deformations. Two deformations of A mu 0. Then we consider mu t, which is equal to sum of t to k mu k from k, and mu dash t, which is the sum ttk of mu k dash, k larger or equal to 0. And here, of course, mu dash 0 is the same as mu 0. Huh? Okay. So I'm saying that these two deformations are deformations of my algebra A defined by mu 0. Okay. Then we say that they are equivalent. We say that they are equivalent if there exists a formal morphism phi going from A to AT. And again here, this morphism should be from AT to A, but I can restrict it to A. Because of the KT linearity, sending an element A to an element phi A, defined to be A plus T, okay, phi of A, phi 0 plus T plus T square, phi square of A, etc.
Are you trying to connect the two deformations by some algebra KT, algebra homomorphism?
Yeah, this is by this phi T. Then if you have this such that mu dash T of AB, the phi T of mu dash T of phi. This is no, this is mu T dash of phi A T phi A. Okay, for any A, B in A. It's enough because of KT linearity. Huh? It says that we have two algebra. It says that phi T is an algebra morphism.
Phi T is phi?
Yes. Yes. Okay. Now let's see what it means if I expand things.
Shouldn't phi naught be some kind of identity? Phi naught, there is no restriction. Because what's preventing phi t from being 0?
Alright, then you notice it is identity. Huh? But of course we can also consider that it's not really done for the moment, but there is some research where this phi 0 is not the identity. Then it becomes tricky.
Can it be invertible instead?
Yeah, it should. Yeah. Okay, then let's see what it means. Then we can rewrite this equation by expanding things. Then what we get is a sum. Then this T to I for phi I, and here a sum over I over k now, T to k, then plus k of mu k of AB, and this should be equal to a sum. And here we have 3 in that's T here. Then it's T to I plus J plus K. And this mu I, phi J of A, and phi K of B. Okay? And we will have a sum here, I, J, K. And now let's see what happened for T0 to T to 0. What is the constant term here? And the constant term is when I plus K is 0 here, which means that we have phi 0, mu 0, and this is And here also I, j, and k should be 0. And here is mu 0, phi 0, okay. I can write it like this. If you composed by phi 0 times phi 0. You understand? And this is exactly, since phi 0 is the identity, then it's satisfied. Mu 0 equals mu 0, which is satisfied. Otherwise, one should just take an algebra morphism. Then we can default up to an algebra morphism here. We can discuss the equivalency with respect to some algebra morphism.
Shouldn't there be a prime at the mu I on the right hand side?
One second.
At the right hand side, the mu I shouldn't have a prime.
Yes, you're right. Thanks. And this is a prime, yes. And this is a prime here. But mu 0 prime is the same as mu 0. Okay, now let's see what happens for T1. Then we have two terms here. Phi 0 mu 1. And this should be equal to plus phi 1 mu 0. And in the right hand side, one of the indices should be 1 and the other 0. And we have three terms. Then it's mu 1 of 0 of, okay, tensor phi 0 plus mu 0 divided by 1 times 0 plus mu 0 composed with phi 0 times phi 1. Now if I take into account that the phi 0 is 0, phi is the identity, then I can write it in this way, and this is mu 1, and I can put this in the other side, and this is mu, again, I should put dash everywhere here, yeah, it's here, then this is mu 1 dash plus mu 0 composed by phi 1 tensor the identity, this, and plus mu 0 of composed with the identity tensor phi 1, and minus the minus phi 1 composed with mu 0. Okay, and this is the condition at this level.
How do we get the tensor product in the second equation? Yeah, one before this, for t equals t0. How do we get the tensor product on the right side?
This one?
Yeah.
Yeah, then here, now I'm looking for the constant term. And the constant term, you get it with the power, with I plus j plus k should be equal to 0. And then the only possibility is when I is 0, j is 0, and k is 0. I will write it in this way, if not mind.
That's what
If I apply to IB, then they apply phi 0 of A, phi 0 of B, and they apply again mu 0. Okay, then have a look on this equation and tell me if you notice something. What about this? Delta 1 of phi. Then this is exactly, then this is mu 1 equals to mu 1 dash plus delta 1 phi 1. This means that if you remember, we have seen that this mu1 should be a two-cocycle. Huh? And again, if I assume that they have the second deformation, this mu1 dash should be also a two-cocycle. And the difference between these two cocycles is a coboundary. What does it mean? Then this mu1 and mu1 dash belongs to the same cohomology class. Huh? Then this is, now we have now we have the third main theorem in this theory, which says that the first term of the deformation depends only on the cohomology class. The first term of a deformation depends only on the cohomology class. Which means that if you take two first term with belonging to the same cohomology class, the deformation will be equivalent. Okay.
So the first term already belongs to some cohomology class, right?
For both.
For both. That is H2.
Yes. This is in Z2. This is in Z2. But since the difference is a coboundary, then two coboundary, then it means that they are in the same cohomology class. And now we have a very important corollary of this. Now, what happened if because what I can go further here. I can see that before this. Then I can always if I have a deformation, I can always write it in this way. Every deformation is equivalent to a deformation mu t equals to mu0 plus t to p, mu p plus t to p plus 1, mu p plus 1, etc., where mu p belongs to Z2, AA, and mu p doesn't belong to B2. And now I have my corollary.
So what we have proved for mu1 here, that what we have proved for mu1, the first terms,
Yes.
also applies to higher order terms, mu k prime, but they like the difference. There are differences in the.
Yes, because I mentioned in the beginning that the first term is always the two-cocycle.
Yes. But our theorem 3 that we just proved says that that mu1 and mu1 prime, they are the second. mu1 is determined only up to the homology.
Yes.
Cohomology.
Yes.
Second homology.
Yeah. And they can show that if it's a two coboundary, then they can up to isomorphism remove it, because it will be equivalent to a term to a deformation where this term is 0.
Okay. So you mean that there is a 0 in that same class?
Yes.
And you
You can replace it by 0.
Okay. So that is okay for the first one. What about the second, mu2 and mu2 prime? The same result holds for that also?
I don't care.
Okay.
Huh?
But in that corollary that we just saw, In that corollary,
This is
last corollary.
yeah.
Then
But this is not a corollary. Maybe but it's in the theorem.
it's another
You
theorem.
can consider it in the theorem. Now I will give you the corollary.
I have a question.
Yes.
Here, regarding your definition of equivalent, the definition itself doesn't seem to imply equivalence. It's only one direction. I mean, you have phi. Shouldn't there be some? You see, you're saying that phi t of mu t is mu t prime of. What about the reverse direction?
What do you mean by the reverse?
I mean, we can write mu t prime in the same kind of thing.
Right. Should there be some other sign that works for?
For what? You mean you reverse mu dashes here?
Right.
Yeah, but this phi t is reversible
I see.
since it starts with the identity.
And that works for the
Yes, of course. Yeah. Since this is invertible. Since it's invertible, then it works in the aspect. And if you have the property I mentioned in the beginning, if you have the first term which is constant, then you can invert this power from a Gauss series. Okay, now the corollary. Now what happens if H2 AA is 0, then if Three-cocycle is a true boundary, then the consequence here is that we cannot have any deformation. Then every deformation, every deformation is trivial. Okay. Then if you compute the homology of your algebra,
So this is coming out of that last theorem.
yes, yes, yeah. Because you can go further. I mean, if this mu p is again a true boundary, then you can remove it by to equivalence, and etc. You can do it.
Yeah, so my previous question was this, that just as we derived from that equation mu1 and mu1 prime differ by this co-cycle, so does the same conclusion hold for any mu p for p greater than 1? Mu p and mu v prime only differ by this co-cycle. So
this is the same here. I mean, for this, you mean this mu p?
Yes.
Yeah, of course. This mu p also. This mu p differs if you take another mu dash p belonging to the same cohomology class, then you get an equivalent deformation.
So the conclusion for one holds for any p.
Yes. And now this is a very important corollary, and we say that the algebra is rigid. That the algebra is rigid. Rigid means doesn't mean that that the cohomology is 0, but it means that we don't have any deformation, and then you cannot modify, you cannot deform. Okay. Then this is but here we have a criterion. I mean, the converse is not true. There is examples where the algebra is rigid and where the cohomology class is not trivial. Okay. Maybe just a few words to end this first talk. And what about maybe example here? Examples. Take any semi-simple associative algebra, any semi-simple algebra as rigid. Okay, then this is. And I should also mention that this theory works for any algebraic structure. That's why in the beginning I mentioned the system algebraic structure. And for example, for Lie algebra, it was done by Richardson. And of course, you have to find a suitable cohomology. And for Lie algebra, this Chevalier-Eisenberg cohomology works. And for some other algebraic structure, it works. But for example, for Jordan algebra, we don't have good cohomology. Then we cannot work out this approach. And maybe a few observations now about unital algebra. Then every deformation like observations, I will end with this. Every deformation of unital algebra is unital. It's automatically unital. You do the deformation. And now what about cumulative algebra? Now let A mu 0 be a cumulative algebra. You mean associative algebra, of course. And mu t equals to mu t t2 k mu k is a formal deformation. Then if you consider the vector space and a bracket where the bracket of A B is the mu1 of AB minus mu1 of BA over 2. Then this is a Poisson algebra.
This formal deformation is an associativity.
Correct?
This formal deformation is an associativity.
Yes.
The mu t we are taking here, that is a deformation as an associativity.
Yes, of course. As an associative algebra. Then this is, I don't know if you know what Poisson algebra means. Then Poisson algebra is a triple where this A is a commutative associative algebra, and this A bracket is a Lie algebra, and we have a compatibility condition, and we have a Leibniz rule, which means that the bracket of A, B, C, like this is A, B, C plus A, C, B. And here, the example I mentioned is this examples from physics. If you take polynomials, algebra of polynomials with pointwise multiplication, then you have examples. Then here, let's say R of x, or functions. Then you can have Poisson algebra. Let me show you the example because I want to say a few words about quantization. Yeah, I mean, this is very important in physics. We take this algebra, and for this we have pointwise polynomials on x and p. It's a position and velocity. And then here we have an example of we take two polynomials f and g, and the bracket is defined to be df of dx, dg, dp, minus df of dp, dj of dx. Okay? And this is the Poisson algebra. Then this theorem says that if we have a deformation, then automatically we have a Poisson algebra.
In the definition, you're assuming that A is a Lie algebra.
Yes.
It has a Lie product. So
Yes.
when you take Rxy, two variable polynomial ring,
Yes.
then we have, what is the Lie algebra structure here?
This one.
Oh, this is the Lie bracket.
Yes. And of course it satisfies also with respect to pointwise multiplication, this Leibniz rule. Huh?
When a Lie bracket satisfies this Leibniz rule, it's a Poisson bracket.
You need also commutative associative algebra. Huh? Okay. Then this is a very important example for physics. And now, and this what physicists call.
We should have stopped at some point. We should have stopped at some
Yes.
point.
Well, 2 minutes. I could take that from the next part.
Then you will have to stop at the right time. It will be difficult to.
Just to mention this quantization, then the problem in physics now is we start now, if we have a deformation, we have a Poisson algebra. Now we start with Poisson algebra. We start with the Poisson algebra. Algebra, for example, this one. And then this corresponds to classical mechanics. And now we want to go to quantum mechanics. And to go to quantum mechanics, we need to deform this product. And to construct, we want to construct new product, a deformation, such that f star j is fj, this is the pointwise multiplication, plus, here let's say mu1 of f and j, t, plus mu2 f and j, t squared, etc., where with my Poisson bracket fj is mu1 fj minus mu1 jf over 2. Then we fix our Poisson algebra, for example this one, and we want to deform it, deform the multiplication, get something non-commutative for the quantum mechanics.
So, do we know there will exist only one such product, or they can exist many such products?
You mean this star product?
Yes, yes.
Yeah, that's a problem also, to classify all this, and this is called star product. And if you remember in the beginning I told you about this algebra of functions, but over a manifold, and this is the case here. And then this was very important for a problem for a long time, and it was solved, for example, for symplectic manifolds. Then we could construct, like it's the case here. Then here we could construct. So for symplectic it was done since a long time. And then the problem was open for a while for general case. And then it was solved by Kontsevich at the end in 1997. And then he gave this the solution. He gave a big theorem which includes the fact that we can construct all the star products for any Poisson Poisson algebra, and he classified also up to isomorphism all this star products. Let me just give you the star product here and then end my course. And this is for example, for this one is the sum, and going from to infinity of dn f dx and dn j dn t to n over n factorial. And this is the deformation.
This is the formula
Yeah, this is the formula for star product.
of Kolsevich. This is
No, not for concept, for this example.
But there can exist other star products in this situation also. Not, this is not a unique one, or is it unique up to some equivalence?
It's unique up to this class, up to this mu one.
Isomorphism class.
Yes, yes.
So isomorphism class is the Poisson algebra.
Yeah. Okay. This shows that this maybe should stop here and see maybe a few words later about quantum groups, which could be also seen as a deformation. Thank you very much.
Okay, so we continue in 5 minutes.
Yeah.
And
Because I need to.
make during that time questions.
Yeah, I need to start also my computer because
Will be
yeah,
like,
projected.